Hey, it's been a while since a video came out on this channel, sorry about that. Today I want to show you how I might build a Lorenz Attractor visualization in GeoGebra, and the reason I'm going to do that one, some of you may already know, is because of a conversation I had with Grant Sanderson from the 3Blue1Brown channel I had recently. If you have never watched a 3Blue1Brown video, for goodness sake go and sort that out. I reckon it's the benchmark of mathematical visualization on the internet at the moment. But we had a chat about how we might make this visualization because Grant was quite keen to showcase on his channel how sort of back-end workflow of how he makes his videos happens. Spoiler, he uses Manim, which is a Python library that he wrote over the years. We had a chat when he was over in the UK, and you can watch a fascinating video of him trying to explain how he does what he does to me on his channel. But I thought I'd try and make the Lorenz Attractor visualization how I often do it in GeoGebra as a useful sort of companion video alongside how we talked it through on Grant's. So without any further ado, let's chat some Lorenz Attractor history and make it happen in GeoGebra. If you look up the Lorenz system or the Lorenz Attractor on Google, get to the Wikipedia page, you'll find a nice little animation going on already. This is the sort of thing that we'd like to end up being able to see that we've built ourselves, and I guarantee by the time we've built it ourselves we'll understand it a little bit better. And you'll realise that the history is kind of interesting here. At its heart, it's a set of three connected differential equations. That three is good because we can use each variable x, y, and z as a coordinate in three-dimensional space, so we can end up plotting something in 3 dimensions. It's important to remember this is a representation of three variables which aren't necessarily space variables. We're just seeing how these three coordinates would plot in 3D space to see how a system evolves. I think in this case Lorenz was trying to plot data to do with the weather. And there's a really important story about how this has triggered a realization that's profound about chaotic dynamics and nonlinear systems, but more on that another time. The important thing for us now is that these three equations, these three differential equations, are going to govern how this system develops, and GeoGebra has a neat way of just dealing with differential equations, which we're going to use as the basis of our visualization. Right, I'm here in GeoGebra. It's a brand new Classic 5 window. I'm using Classic 5 because it gives me a slight bit more functionality when I'm working on a PC to move windows around and sort of take them out of the main window and undock them. And Classic 6 doesn't do that. But it's really only for irritating users like me who like having more control stuff. If you want to just use the browser version or Classic 6, which look very similar, all the mathematical functionality is going to be in there too. You won't be able to do things like pop out an algebra window to keep it separate. That seems to be the only thing you can't really do. And because I want to be able to do that, I'm going to work in this version, which I'm very familiar with. It starts off with just a graphics view and the algebra view. I would like to get some three-dimensional view as well, so I've just turned that on. I'm going to keep the graphics view, 2D view there as well, although I don't want to plot very much on it. I can use that to put sliders on and things. In the browser version, you might recognize that the sliders turn up in the algebra window, and they don't in this. So there are some irritating differences between the versions. We're just going to deal with that. Okay. First things first, though, if you remember the equations we just saw, they have some x, y's, and z's in them, and then we're going to represent them on the three-dimensional axes, and some other parameters. So we're going to set up those parameters, and they use Greek letters. So I'm going to use the same Greek letters as the Wikipedia page, and they are beta, rho, and sigma. Let's do it in the other order. I'm going to put sigma in first. I typed sigma by pressing Alt-S, so useful shortcut. You can always get Greek letters by clicking on this thing, and you can pop the Greek letters up there. And I don't really know where I need this to go between. On the Wikipedia page, they let sigma be 10 for the visualization they used. I think Grant and I did that the same in his video. So let's let this go up a bit bigger than 10 with some little increments. Anyway, that's going to be our sigma slider. It doesn't do anything yet. It's just a parameter. In fact, what I'll do is I'll set it to 10 because that's the suggestion in the Wikipedia page. We also need a rho. The annoying thing about rho in GeoGebra is that I want Alt-R to do it, but it doesn't do that. I get a performance overlay if I do that, and sometimes it does a square root symbol. So I'm going to have to use the little menu. Frustrating. GeoGebra, do you want to implement a rho shortcut, please? Thanks. And this time they suggest rows 28, so I'm just going to let it go between 0 and 30. I have no idea really what it's representing. And let's set it to be the 28 they suggest. And finally I need a beta, and Alt-B does beta, and beta on their suggestion is 8/3, but let's let it go up to 10. Maybe that's too high, don't really know. And let's set beta to be 8/3. Okay, these are parameters set. I don't really want to change them yet. But the nice thing about building this in an interactive piece of software like GeoGebra is that when we do build the thing, if they depend on those parameters, we should then be able to change them and see the whole system change with it. That's for later. Now we need to get the differential equations in, and this is the bit that you may never have tried to solve differential equations in GeoGebra. You can do it numerically. It solves differential equations numerically, like all mathematical software sort of needs to do. Most differential equations you don't get to solve analytically. You need to use a numerical method. I think it's using a Runge-Kutta method, but again, that's kind of above our pay grade today. We need to get the equations in though, and I'm going to type them in as functions which depend on several things. The functions are going to depend on the three variables x, y, and z I've already mentioned, but also time, because they're going to evolve over time. So let's set that up. I'm just going to put them into GeoGebra as functions. However, they do need to have these functions of all the variables, so I'm going to call them x dot. GeoGebra doesn't know what x dot means, which may be a good thing. It's just going to be a name that I know what I'm referring to, and I need to tell it the variables, which are t, x, y, and z. So 4 variables in this function before I tell it even what the function is. And if you remember the equations, we need the sigma, which we've already defined. I'm going to use Alt S and then y minus x. That is the x dot function, and let's just make sure we can see that. Okay, there it is. Let's do y dot. Again, I need to select the 4 variables, and this time the y dot function, dy by dt, if you want to say it properly. I need the row. Now it's under my face here, but there's a little alpha symbol. I can pull out the row symbol out. Again, don't know the shortcut. If there is a shortcut, someone just tell me, that would be good. Take away y. I think that's the y dot equation. Again, make that visible. And z dot, function of t, x, y, and z, is x times y minus beta, that was old b, times z. I think it'll recognize beta z if I type that in. Good. So these are the basis of all our setup. These are the 3 differential equations. Now the magic happens when I tell GeoGebra how to use those 3 functions using a differential equation solver built into GeoGebra called nsolve. So let's see if I start typing that. In fact, nsolve can solve equations as well. There's an nsolve ODE, that stands for numerically solve an ordinary differential equation. You can see why they shortened it for typing that command in. And if I hit return, it's going to populate my input bar, and it's important to pay attention to how it wants the setup here. And there's a few things I actually need ready to get in there. The list of derivatives is going to be a list of the things I've just made. I need an initial x coordinate. Now careful here, the x coordinate this command wants is kind of the horizontal coordinate of what it's going to plot its results against. And that's going to be time for us. So confusingly, in this language, the x it's referring to will be time for and the initial y coordinates, plural, will be x, y, and z. They're the sort of the outputs of the 3 variables in our system. So I'm going to need an initial x coordinate, and that might matter, so I'm going to make something before that. And I also need to tell it its final x coordinate. There's like how long to solve this equation for. Don't go indefinitely. It's not solving it analytically, remember, it's solving it numerically, so it needs to stop at some point, otherwise it will just carry on doing it forever. So I think there's 2 things we need to set up first. So let's delete that. Let's set up an initial point. I'm literally going to make a point on the screen. It's called A. You can move it around. And it doesn't really matter where this is to start with. Maybe I'll just tell it to start it at 1, 1, 1. It would be tempting to do 0, 0, 0, but I think quite often the differential equation or things that have start 0, 0, 0 never do anything interesting. I think that's true in this case. So 1, 1, 1 feels a little bit off the 0 problem, but it could have been anything else. And actually, because it's a point, maybe I can move it later and hope that it updates what's going on. That's the dream. We also need to deal with this time issue. In particular, the maximum time I want it to go for. So I'm just going to call a variable called max t. When Grant and I did this, we picked a time of 30, somewhat arbitrarily. I'm just going to pick 30 so it kind of matches that. But this is just how long for this version of time in these equations to carry on checking for the solutions. And we can change that later, I hope, as well. Now those things are in place. It's helpful to have them in place first so that when we start typing nsolve, we can refer to those things. Let's try it. Nsolve ODE, the list of derivatives is going to be a list of those functions. So I think the order is important here. You'll see why you need to recognize the order, but x dot, y dot, z dot, and I've put them in curly braces to tell GeoGebra that's a list of things, and it wanted a list because it said so. The initial x coordinate, remember in this language the x coordinate is like the time for the x coordinate of how it display the outputs, and I want that to be starting at 0. And the y coordinates, well, they are the starting points of my plot, and that A point I just made is meant to represent the x, y, and z starting points. So slightly irritating, I need a list of the coordinates. So let's make a list, and grab the bits of the point called A. Annoyingly, x of A is what I'm grabbing the x coordinate, and then the y of A grabbing the y coordinate. I don't know what's putting extra brackets in there for me. And then z of A. Oh, it's typing the bracket for me, and I keep adding another one. I wish it could just take the point. It might well have been able to take the point, but that's, I know, going to extract the x coordinate, y coordinate, and z coordinate of A and put that in a list. So that should be fine. And lastly, the final x coordinate is like our final time, and I made max t for that exact reason. Even before I press return, something has happened on screen. It's basically trying to preview the output here, and this is kind of all the grunt work done for us. Hit return. It has made 3 numerical integrals. Unhelpfully named perhaps, but 1, 2, and 3, and I think that's why it's going to be important to remember the order you put those 3 differential equations in. So 1 is going to refer to the output for x, because the first differential equation in there was x dot, 2 for y dot, or y rather, and 3 for z. Let's have a quick look at what it's doing. You can see it on this. You can see some funky looking graphs. Let's just give ourselves a bit of space. Wow, they are funky looking. Basically, there are 3 of them from 0 to 30, and that was our time coordinate, if you like, and it's plotted on the x coordinate. Let's just hide a couple of them. The first integral it's done is solving the differential equation for the x variable, and it's saying as x changes over time, it's going to look like that. Now, that's surprising in its own right. You might not recognize that from the earlier animation. This is because it's just the x coordinate of the output, and we've also got a graph for the y coordinate. It looks very similar actually, and the z coordinate, which is up there somehow. What I'd really like to do is get those 3 things turned into a point in 3D space so we can see how it moves around, and that's going to be our next battle. I think we can probably hide these for now. As interesting as those graphs are, I want to focus on getting a 3D representation. They do appear to be still there on the 3D graphics window, and this is something to bear in mind with GeoGebra. I'm going to select all of these, click on properties, and in the advanced tab for any properties, if you scroll down, you can choose which displays any object turns up on. And I don't want those things to turn up in the 3D view. I don't really want them on the graphics view either, but I'm just kind of belt and braces turning them off in there. So we'll just leave them there, and I've hidden them with this dot. Okay, so far so good. It's done the work. Now we've got to do the work to tell it how to plot those 3 graphs and turn them into a 3-dimensional point. And that's our next job. So our task is how to get GeoGebra to recognize these 3 things as coordinates at a particular point in time. And it's not entirely obvious how to do this. Let's focus on numerical integral 1. In fact, before we do anything else, I'm going to rename these so I don't have to figure out which is which. I'm going to call this the x coordinates. I could just call it x. I'm going to call it x1 in case I do another solve for a different starting point, which, spoiler, I'd like to do because that's kind of the point of this chaotic system. So let's call this x1. It's a list of the x coordinates over time of this solution. So that's just called x1. Number 2 would be the y1, and now it's going to be much easier to recognize which is which. Why have I called it y2? Let's not do that. y1 is better, and z1. The 1 is standing for the fact that I think I would like another solution from a different starting point later, which I'll probably call x2, y2, and z2, assuming I remember that plan. Okay, so it looks like this is a function, but it's not. It's actually, if you double click on it, you can see it's a locus, which means it's basically just a line in GeoGebra. And therefore, I can't just say, like, give me the x value when t is 10. I don't think I can. Let's try it. x1. If it was a function, I could put an argument of 10. And no, it doesn't know what to do with that. If they were functions, I could just do that, but they're not. They're just kind of a line. So it's slightly awkward trying to pull out the coordinate. Let's say I wanted the x value at 10. How do I get it? Well, if it's just a line, there is a very useful command in GeoGebra called point, which puts a point on an object, and the second version of this is a point on an object with a parameter, and all that means is it uses some built-in parameter to move that point on the object from the beginning of the object to the end of it. In this case, that object x1 is kind of a line. It started at 0, ended at 30, and using a point on x1 like this, if I put a parameter in here, is going to move that point around it. So let's make a parameter called t. I'm going to go from 0 to 1. I know that's not our time, but I'm going to give it a tiny increment for now. So that's kind of like our proxy for time. It doesn't do anything yet, but if I type in x1 with a t, the reason I'm using 0 to 1 is that parameter should be from 0 to 1 in GeoGebra, and it goes from the end to the beginning to the end of the object. Let's press return. It's made a point B, which moves around that. And now I've got access to the value this takes, as if it was a function, is going to be the y value of that point. Now I don't have to do this like make the points. I could just refer to a point on that object with the parameter, but maybe it's useful to keep them there. So let's rename that to be an x point or something, and I'll do something similar for the others, so I can easily grab hold of a sort of version of this. I'm a little worried it's not going to make a coordinate. Oh well, now let's use the command point, this time on y1 with a parameter of t, and let's do a z point, which is going to be point on z1 with a parameter of t. And now they're always going to have the same x coordinate, which is kind of irrelevant because it's the same as t. Well, actually, it's not the same as t. It's kind of t multiplied by max t. That's going to give us our sort of real time. The other thing with this, well, let's just work like that for now. I'm now able to extract the values at any particular time t. Well, let's turn that into a point in 3D space. A is my initial point. What I want to, instead of seeing these dots zip around on the plane, which they're kind of doing over here, I don't really need to see them. What I want to do is make a new point in the 3D plane, 3D space rather, that has x coordinate of the y value of the x point, y coordinate there, and z coordinate there. Let's just do that instead of talking about it. I want a point which is the y value of x point, the y value of y point. The naming terming here is confusing me. Even just words are confusing me. I think you get what I'm going with here. The y value of z point. Let's see if that works. Now, point B is possibly not visible on screen. It looks like we need to zoom out a bit. I'm using my mouse wheel to do that. There is point B. Okay, the magic would be then if I move T around, does B move around? Yes, it does. It looks like it wiggles a lot. How exciting. I'm excited. I don't know if you're... What I really want to do is see the line as that moves. So there's several ways to do this. One, maybe an obvious way to do this is to use the locus command, and that's what kind of GeoGebra has done in the background for these things. You saw that it was a locus earlier. The locus command you can get from a tool in here, and if you hover over it, it says select a locus point, point on object or slider. There's also a written command, which is, in my opinion, more helpful because you can see the various versions of it. And what I really want to do is make B make a line as T moves around. So actually, let's just use the command. B is going to make the line as T moves around. I'm already excited. There is the locus of point B as time evolves. And what we should also be able to do is just let T animate now, and we'll see it whizzing around this system. This is kind of the holy grail done already. We've made a visualization of what the solutions to the Lorenz system do in three-dimensional space. And it's something of a surprise that this system looks like this at all, I think, to me, and maybe even to Lorenz. This is incidentally one of the reasons why we think part of this discipline gets called the butterfly effect, because this particular system looks like a sort of weird squashed butterfly shape. There's other reasons why you might call it the butterfly effect, but it does seem to be several layers to that name. Now this is great. What I'd really like to do, a little bit like we did in Grant's video, if you haven't seen that, go and watch it sometime, is not see the whole path at first. I kind of want B to trace it out so we can see it evolving over time. And I think that's going to be easy enough to do. Let's have a quick think about how to do that. At this point, I want to give a big shout out to Juan Carlos on the Beauty in Math YouTube channel, who's been doing some really lovely stuff, visualizing lovely maths, like we're all trying to do here, it seems. But he did a particularly lovely tutorial on how to plot the Lorenz Attractor in GeoGebra, which made me suggest it to Grant in the first place. So kudos to Juan Carlos for doing that, and his video is absolutely worth watching, which is where I got most of the crucial ideas of how to make the right implementation happen for this. Great work. I think the problem we have is that the locus object we've just made isn't that flexible. I can't sort of chop bits off it very easily. It'd be much easier if the path I was plotting there was just a list of points which I could take the first few of or the first next few of, and then it's very easy to just take as much as or as little as I want of it. So we might need to do a bit of work to turn the solution into a list of points instead of this locus. So let's ditch what we've just done. As amazing as it was, let's kind of build an alternative format of this solution. So let's build a list of points that represent that locus. And we can do that with the sequence command. This is a super powerful command in GeoGebra and in any programming language that lets you access lists and arrays. Handling how to generate a list is important. In this case, I want a list of points that come from the values from x1, y1, and z1 at various points through it. This is going to feel slightly awkward to get out, but I would like a point. So that's my expression I'm going to generate is a point. It's going to have 3 values in. So those are my commas in there, an x coordinate, a y coordinate, and a z coordinate. And I'm going to use a variable k running from 0 to 1. The catch is I think its step size needs to be quite small. So let's put something in there I don't know about yet. So this is the way a sequence command works, is you type in an expression and then let it generate that expression as a variable. In this case, k runs between the things you set up. And I'm going to use k as the parameter on the point command, which I used earlier, but we're just going to type it straight into here. So the x1 is a solution. I'd like to grab the y coordinate of x1 at a certain time. So y of a point on x1 at parameter k, and that k is what's going to march through it. I think that will do it. So let's do something similar for the y coordinate. So it's y again of a point on y1 at k. Close all those, and let's do something for z. And so the first y in there is grabbing the y coordinate of that plot. Remember, the x coordinate is time and the y coordinate was the height of x, y, and z. Again, we're running into this confusion of x, y, and z being used for 2 different things, but once you get past that, I think it's okay. So it's going to grab a point from z1 at point k, close those 2 brackets. I think that is now the point I'm building. So I just got to sort out this step size. Now, this is where it would be quite useful to know what resolution GeoGebra actually has in the background for this locus. And we could find out the length of that object as it's stored in GeoGebra, and that'd be one way of picking a resolution. But this is essentially how small do I want to step through it. So I'm just going to go as a tiny step size, and maybe I can change this later. Let's put 5,000 in there, so that the entire path from 0 to 30, which I've already kind of got solved in those functions, is split into 5,000. And actually, the step size is not 5,000, it's 1 over 5,000. It's already done something. I kind of hate this preview thing, because if you get something wrong, it tries to do something horrendous, and when you're dealing with lots of points, that might be a problem. In this case, it looks kind of what I want. So let me press return in the faith that it will actually do it. There we go. We have made a list. It looks like it's a list of points. I'm curious about why it's starting there. It doesn't matter too much. Oh, it's because I've moved A around. That's interesting. I thought A was at 111. We can put A back to 111. And then I was expecting to see 111 as the first point in the list. And there we have it. And it's done it. So it's made the locus, but from a bunch of dots. And that doesn't look very pretty, but I think it's super flexible. So this list is now the list of the whole solution up to max time. What I could do is just hide that and grab the first n elements of it. In fact, I haven't used this. Remember, this t is what we used earlier. This list is all of it from 0 to 30. So I could use t to grab the right amount of dots from it. Let's do that. I'm going to use the first command, which is a way of grabbing the first number of elements from a list. Let's first from L1, and the number of elements, how do I want to get that? Well, I need how many elements are in L1, which is length L1. I'm not quite sure what I'm doing with that yet, but that will be in there. That will grab all of them, but I just want to kind of multiply t times that. Now t is going to be some number between 0 and 1, so I presume it's going to deal with the fact that t is not always going to be a whole number. This number, let's just see what it does. I think it's doing what I want. I haven't really worried too much about letting GeoGebra sort out those things, but that's kind of letting the thing evolve over time. When t is 0, we get an empty list, but that's... I don't really want it to disappear entirely. I guess it's not a problem. What I do want to do is make this look prettier. So let's establish the fact that I've now got this L2, which is the generating list, and it's controlled by t to get its length, and hide it. And I want to make a line out of a bunch of points. And there's a brilliant command in GeoGebra called polyline. It just wants a list of points. I'm going to give it the list L2, and it will make a line of points. Or rather, it joins all the points up. And because we've got quite a high resolution of points, it does look like a curved line, although, spoiler, like all lines on sort of vector graphics setup, it's a bunch of straight lines. But that does generate over time. And hey presto, we've got a generating Lorenz system. In fact, let's have a look at how pretty it can be. Let's let it animate. And we can even let this spin around as it goes. This is kind of the effect I was going for. And in GeoGebra, it's easy enough to get the solutions. You have to think a little bit hard about how to get them to plot in 3D, and maybe a little bit harder about how to get it to generate over time. But it's doing what I want. It's going backwards. I don't really want it to go backwards, so let's change the properties of this to just increase. And we can change its speed here if we want it to go through that whole cycle a bit quicker. That's fine. These are all adjustments you could make over time. And you're seeing something nice about the Lorenz system here. You're seeing that it starts from a point and it goes around into this spirally thing and then sort of occasionally flops onto another wing of that spiral in a way that's not very predictable. This is what they call a strange attractor. There is a sort of shape in the background here which all solutions to this system seem to end up in. And actually we can check now. Let's stop this thing spinning. We can crank this up to there, but let's move the initial point around. This is the advantage of having an interactive piece of software. It's solving different differential equations, different starting points each time, but every time I move this, it does seem to create the same sort of shape, just different starting points give you different, slightly different outcomes. And I guess this is one of the points of a chaotic system. A tiny difference in starting conditions leads to a massive difference in output. And that's not what we're seeing. We're seeing the same thing. And so this is the paradox of chaos. What we're seeing is that it's the same rough shape, the same strange attractor, but actually the outcome is very different. It just happens to form into a similar shape. Now, to really emphasize that point, what we should do is solve this again for a slightly different initial condition, and let's see them generate at the same time. That would be the sort of goal of what we're trying to develop here. So let's try and make that happen as our final goal. Our initial condition was this A point. It's not very helpfully named, but it doesn't matter too much. Let's make another point. Well, actually, we don't even need to make another point. Let's just solve the equations again with a different initial condition that's only slightly different. And let's type in nsolve and do it all over again. List of derivatives is going to be exactly the same. But tell you what, by the way, you can always get a list of history commands, by the way. Scrolling down here, there's the command I used earlier. I might as well reuse that. But I don't want it to solve the exact same system. So let's just add a tiny amount to the Z coordinate. I don't know if that's going to be enough. Everything else is the same. Press return. I need to do the work of hiding this again. I don't want those graphs to appear, but I do want let's do the same list commands. So if you didn't catch it last time, let's do this all over again. Let's make a sequence. In fact, let's grab the command again. By the way, I clicked on the arrow underneath my face. Sorry. If you just press down, you can get the history commands, and I think that's the one we used. This time though, can't do that yet. I need to rename things, so let's rename. As I predicted, let's call this X2, Y2, and Z2. And now let's go and find the command we used for sequence last time, but we'll just change the 1s to 2s, and that shouldn't be too hard. Ooh, made a mess over there. I do kind of like the preview, and I do kind of hate it, and definitely have run into trouble when I've been trying to type the right thing in, but keep getting it wrong, and it keeps trying to preview it and going haywire in the preview. I think I did a resolution of about 5,000, and there we go. Now, interestingly, it does look like the same shape, but because the dots are all blocky, I can't really see if it is different. That is a new solution. It's the full solution. Let's hide it and just get the part solution. So it's just the first elements from there, and let's go L3 t times length of L3. It's very useful having a parameter between 0 and 1 because you can do this scaling thing. Didn't like it. Len is a sensible command, but it's not a GeoGebra command. Is that a Python command? It probably is. Grant, you've ruined me. And I do want to show you that one. No, I don't. I want to get a polyline of that. Now I could have done all this in one command, but it's hopefully useful for you to see it being built. So polyline of L4. And I want to see that develop. Should we just animate and see what happens? There's just one line coming out. I really need to see a point tracking this out, and that seems to be quite essential for us to see, and it would be helpful of the different colors too. So let's sort the colors out first. Quick shortcut for colors. Let's go red and blue, and let's just solve the problem of getting a point at the end of the line. I mean, it's the last element, I guess, of those lists. Last. of L2. Look, that command seems to work. Last of L2 is a point there, and last of L4 is a point there. At the moment, they look quite close together. I'm going to animate it now and see what happens. It's going very quick. Oh, they do look like they've separated. We need to slow this down. Let's see what happens again. Oh, they've separated. So it's possible that I've got too long a window to see here, then it's all going too quick. I could just maybe let's just slow it down, shall we? Even more. And let this go again. Reset it. You know what? I'm just going to hide the graphics view for now, so we've got a much better 3D graphics view. But now I can't animate it. Let's just do it from there. There we go. Now they started with very, very close initial conditions, and they're tracing the same path at the moment, but not now. They suddenly split, and now it's really unpredictable where they're going to go. And yet they're still forming into this butterfly shape. Okay, I think that's kind of the demo I wanted to be able to do. What you'll notice if you've watched Grant's video, or you go and watch it, is that it's much easier to make the aesthetics look great in something like Manim, which is the whole point, was designed to make a visualization look classy. At least, maybe Grant wouldn't say that, but I think that's what's happening. It's kind of the definition of a 3Blue1Brown maths video. It's classy visualizations. What's really good about GeoGebra is that it keeps the interactivity, so even though you can see that in Grant's video, he's kind of got that in his Python workflow too. GeoGebra is designed for that, so you can spin the graph around. Let's pause the animation. I'm going to bring the graphics window back, so I've got these sliders still to play with. Tell you what, let's turn these things off, because it's kind of all I'm using this graphics window for is a slider control window. Tidy that up a bit. And pause things. But the nice thing here is I can drag the initial condition around, right? And you can see these 2 points generate solutions depending on where the initial condition is. Everything is built in interactive, and I'm quite pleased that GeoGebra is able to hand lots of points. So there's 5,000 points in each of these lists, and it's not giving up the ghost yet. I'm sure we could probably make it give up the ghost, but that's really kind of what we're going for. What we should do, though, to try and keep up with the Manim community is make it look nicer. So let's spend the last bit of the video just tidying up the aesthetics. Okay, one of the main reasons I was using Classic 5 was I could do things like this. I can pop out the algebra window so I can still see it, but I'm going to drag it off the screen that you can see. So I've got a cleaner window that I can work on. It's just got the graphics in it. I could do the same, by the way, with this graphics panel, which has got all my sliders on. And I can just have that off screen as well. So now I've just got the 3D view. Now you can't see what I'm adjusting, but the view is nicer. And actually, if you upload that to the GeoGebra materials website, then the main window is all you get given up there. And so it's a nice way to make clean visualizations. I think I would like to make this have a dark background. This is pretty standard stuff. Right click on the background, choose background color. I'm going to go not quite black in case anything black just disappears. And I want to grab it again. The plane underneath it I probably don't need, so that's that button there. The axes are useful, I think, to give us a sense of the space. Maybe I can zoom in a bit. The nice thing would be to... It was obvious when the plane was on, like the perspective is weird, particularly when you make the whole thing. Now that line there and that line there are parallel, but they don't look it to me because I'm used to seeing in the three-dimensional world parallel lines narrow. Parallel lines are not parallel because of perspective. The nice thing about the 3D world in GeoGebra is that you can just choose to put perspective on, and I feel just a lot healthier looking at a 3D view that has perspective on. There are some times when you don't want perspective on. The video that I made about the Penrose triangle needs perspective to be off to keep the illusion alive of an impossible object. This one, I just prefer having it on. So it's already looking nicer, and maybe it's looking more like Manim. That's not really the only goal in life, but I'm going to use my middle mouse button to drag this down because I don't really care about the positive axis, and I can zoom in a bit to make this look nicer. And off screen, I'm going to reset the time to 0 and animate it again and just see how we're feeling about this. So all the things to do with the speed you saw me controlling earlier, this particular initial condition looks like it circles for a while on that one lobe of this thing and then splits over there, and then the two solutions separate. With the dark background, it might be better if it wasn't blue. Let's make it yellow so it to stand out a bit. I mean, it's horrendously garish, but at least they're different And I have a slight colour vision deficiency, so I'm probably not even seeing the same colours as everyone else. But hey, if you're coping, I'm probably coping. The other thing with a three-dimensional view is it's really nice to have it spinning. Now you can kind of just drag and throw it with the right button on a mouse. There's also a control up here. You can click it and it will spin, and you can then control the speed of it, and that's nicer to have a bit more control over it. And if you drag it to the left, it goes the other way. You can do it with a scripting command, but what I think I'll do is I'll probably stop here and I'll upload a version of the file that has a few more buttons on it, and if you care about that sort of level of detail, go and download that file and reverse engineer how those buttons are doing it. Spoiler, it's just a scripting command in the back of GeoGebra, and the GeoGebra manual has all those commands if you want to go and look them up. Okay, this is good. The one thing I will say is that I don't think it's as good as what it looks like in Manim, and there are several reasons for that. We're paying the price of working in an interactive GeoGebra window. It's not as efficient at just computing stuff, and a lot of people complain that Python's not very efficient either, but it's much more efficient than GeoGebra. However, the fact that it's still doing this, it's doing a numerical solution of differential equations, it's doing it twice, putting 5,000 solution points in it, and it's still able to spin the thing around while it's animating, I'm pretty happy with that. The things that you'll see on Grant's video, like making the dot glow and look nice, these are all actually really important upgrades to make a visualization look pleasing, and it's much harder to do that in GeoGebra, which is why things like the Manim library is a good thing to explore if you want to go pro level visualization. But the sacrifices have some gains. We have interactivity here, we can move the initial conditions around, and we can see this thing generate with a sort of slider that you can grab and hack around if you want to, and that has some value. I would say the value is that you kind of feel like you're getting your hands on the maths. Surprisingly important in my educational experience to feel like you can get your hands on something. I'll leave you with some visualizations that I've made using this exact thing. Hope you've enjoyed this. See you next time for another build on GeoGebra, probably.